Title: The $175 M Shattered Mirror. How Shenzhen's tallest illusion rained terror from 800 feet Copley Tower Disaster. An act of unchecked ambition. Imagine walking through the bustling, hyper-dense core of Shenzhen's Futian district. You are surrounded by gleaming monuments to economic dominance, but one tower stands above the rest. It is a masterpiece of modernism, 790 feet of unbroken, blue-mirrored glass that appears to melt directly into the Guangdong sky. It was supposed to be a statement piece, a $75 million mega-project designed by the country's most celebrated architectural minds to make every other high-rise look like a warm-up act. Instead, it became a 60-story guillotine. This is not a story about a few leaky windows or minor foundation cracks. This is the terrifying reality of the Copley Tower, a luxury megastructure wrapped in 10,344 massive panes of glass, each weighing a staggering 500 pounds, as much as a commercial refrigerator. And in the winter of 1973, those 500-pound sheets of mirrored glass didn't just crack. They tore loose from the structural frame 60 stories up, exploding onto the crowded sidewalks of Shenzhen below. For 4 agonizing years, the Municipal Construction Commission was forced to completely shut down the avenues surrounding the tower every single time the wind hit 45 miles per hour. Think about the sheer absurdity of that reality. A finished, award-winning skyscraper that citizens had to be physically protected from. 10,000 panes, 500 pounds each, an entire financial district paralyzed by a moderate breeze. Behind the chaos sat a single question the developers could not answer out loud. Why was their architectural masterpiece tearing itself apart? The architectural vanishing act. It began in 1967 as an uncompromising act of corporate hubris. The Hangxin Mutual Life Insurance conglomerate decided it needed a towering headquarters in Shenzhen, a statement piece planted right in the historic Back Bay district, a prime waterfront zone undergoing massive redevelopment. The lead designer, a brilliant visionary named Henry Cobb, known to his peers as Harry, wasn't interested in traditional, heavy construction. He wanted to build something that almost wasn't there. His layout was radical for its era. While most contemporary towers featured heavy concrete columns, visible exterior frames, and thick dividers between floors, Cobb chose the absolute opposite: a flawless skin of tinted blue reflective glass, visible exterior mullions or chunky dividers to break up the surface, a rectangular floor plan warped into a sharp parallelogram, sharpening 2 of the corners so the entire 790-foot slab looked like a knife standing on its point. When the sun hit the structure, the tower turned into a slab of transplanted sky, a ghost building disappearing behind the reflections of old Shenzhen. Critics hailed it as the ultimate triumph of modern architecture. But beneath the hype, a deep practical fear was brewing among seasoned structural engineers. The landfill plague and the first cracks. The Back Bay district of this coastal metropolis is not natural, solid bedrock. It is a massive expanse of 19th-century maritime landfill. Soft, saturated, shifting soil. It is the exact kind of unstable ground that makes structural engineers incredibly nervous about heavy vertical loads. By 1972, as the building neared its final height, frantic rumors rippled through the local housing bureaus that the massive tower was actively sinking into the muck. Hangxin executives rushed to issue denials, but the true crisis was happening on the building's glittering skin. The glass was not standard material. Each window was a highly advanced, state-of-the-art insulating unit fabricated by the automotive and industrial glass titan Libby Owens Ford, dubbed Bondermedic Veritron. Each unit consisted of 2 heavy panes sandwiched together with a hermetically sealed pocket of air between them, featuring a micro-thin reflective coating bonded to the inner surface. On paper, it was a thermal masterpiece. In reality, it was a ticking engineering time bomb. Here is the science in plain language. When the intense southern sun baked the tower, the air trapped between the 2 panes expanded violently. When the temperature plunged at night, the air contracted. Normal double-paned windows are engineered to flex slightly to absorb this relentless thermodynamic cycle. But on the Copley Tower, the chemical bond holding the reflective layer between the panes was catastrophically stiff. Instead of cushioning the movement, It transmitted the immense mechanical stress directly into the outer pane of glass. Engineers call this thermal fatigue. The glass was literally being flexed to death from the inside out, in slow motion, before a single tenant ever moved in. The first cyclone fractures appeared in 1972 during late-stage construction. Project managers waved them off as isolated flukes. Then came the terrifying night of January 20th, 1973. A massive winter gale ripped through the coastal delta, sending localized wind gusts screaming past the upper floors at 75 miles per hour. The Copley Tower began to shed its skin, wool 500-pound panels ripped free from their frames, hurtling down the face of the building. As they fell, they smashed into the windows directly beneath them, triggering a catastrophic chain reaction across 60 stories. By morning, dozens of panels were entirely gone. In the months that followed, the count of shattered, falling panes climbed past 65. By April, over an acre of the tower's pristine, multi-million-dollar emerald exterior had been replaced by crude sheets of black-painted plywood. The proudest monument in the city had been reduced to a national laughingstock. The Plywood Palace, and the silent engineering, chronology by May 1973, the Copley Tower was no longer an architectural marvel. It was a 790-foot tall hazard zone, bleeding millions of dollars a day. While the public looked up at the surreal patchwork of mirrored glass and black-painted plywood sheets, a desperate, high-stakes engineering forensic investigation was launched behind sealed doors. The local housing bureaus and the Municipal Construction Commission demanded immediate answers. But the technical timeline they uncovered revealed a cascading series of micro-failures that had been building up for years. To understand how a project of this scale completely derailed, we have to look at the rigid engineering data and the timeline of the construction cycle. October 1967, the Hankson Mutual Life Insurance Conglomerate approves the radical parallelogram design. Ground is broken in the soft mud of the Back Bay Landfill District. Initial geological surveys indicate that reaching stable bearing strata requires driving massive steel H-piles deeper than any previous project in the city. Over 3,000 heavy steel piles are hammered into the shifting water table. Late 1970, structural steel reaches the 30th floor. The concrete volume poured for the central core surpasses 45,000 cubic meters. However, site supervisors logged the first anomalies, minor, unexpected lateral shifts in the alignment of the structural steel. The tolerances are within legal code limits. But the building is proving to be incredibly flexible under standard coastal wind loads. Mid-1971, the first shipments of the state-of-the-art Bondermetic Veritron double-pane insulating glass units arrived from the factory in Toledo. The installation of the 10,344 panels begins at a rapid cycle of one entire floor every 3 days. March 1972, with the tower topped out at 60 stories, the first internal site inspection reports a bizarre phenomenon. Workers on floors 45 through 60 are experiencing severe motion sickness, dizziness, and nausea on windy days. The tower isn't just swaying, it is experiencing a long, slow, low-frequency oscillation that acts like an invisible ocean wave. July 1972. The first spontaneous window fractures are logged on the south-facing facade. Inspectors blame localized construction impacts or improper installation tolerances by the curtain wall subcontractors, H. Robertson. They replace the broken units with identical spares, completely missing the underlying thermodynamic flaw. The science of thermal fatigue. When the forensic engineering teams from the China Academy of Building Research and independent labs finally began testing the failed units, they realized the tragedy was baked into the glass at the factory. The internal airspace between the two 1/4-inch thick glass panes was exactly 1 2-inch wide, filled with dry air to prevent condensation. To provide the mirror effect, a reflective metallic oxide coating was applied to the inner surface of the outer pane. To seal this sandwich together, the manufacturer utilized a highly rigid, lead spacer solder-bonded edge. This was the fatal link: outer glass pane, rigid metal solder bond, inner glass pane. V. Absorbs solar heat, stays cooler, tries to expand rapidly, resists expansion. Catastrophic stress. bond is too stiff to flex. Outer pane shears and cracks. When the intense coastal sun hit the blue facade, the outer pane absorbed massive amounts of heat, causing its temperature to skyrocket to over 60 degrees Celsius. It tried to expand rapidly. The inner pane, shielded from the direct heat and cooled by the building's internal air conditioning, remained stable because the lead solder edge bond was completely rigid and unyielding. It utterly failed to accommodate the differential movement between the two sheets of glass. Instead of flexing, the solder bond acted as a mechanical lever, concentrating thousands of pounds of shear stress directly onto the edge of the outer glass pane over months of hot days and cold nights. This cyclic thermal fatigue created microcracks along the perimeter of the glass. The moment a strong wind hit the tower, those microscopic fractures instantly propagated across the entire surface. The outer pane would shatter into thousands of razor-sharp pieces, or worse, the entire 250-pound outer sheet would detach completely from the internal frame, leaving the inner pane exposed and creating a vacuum that sucked the remaining structure apart. These secret wind tunnel crises, the glass continued to rain down into the public square throughout 1973. The Hongxin Corporation quietly hired William Le Mesurier, one of the most brilliant structural minds in the country, to analyze the building's overall structural integrity. Le Mesurier didn't just look at the windows, he ordered an emergency, full-scale aerodynamic analysis of the building's unique parallelogram shape inside a specialized wind tunnel. What the sensors recorded shook the engineering team to their absolute core. The data coming out of the wind tunnel wasn't about the windows anymore. It was about total structural collapse. The wind tunnel tests proved that when high-velocity winds hit the acute corners of Henry Cobb's parallelogram design, the air didn't just flow smoothly around the building. It created massive, alternating low-pressure vortexes along the sides, a phenomenon known as vortex shedding. Because the tower was designed to be incredibly sleek and light, these aerodynamic forces were causing the entire 60-story steel frame to twist violently along its vertical axis. The calculations revealed a terrifying reality. Under a maximum design coastal typhoon, the dynamic twisting forces could exceed the yield strength of the main structural steel columns. The building wasn't just flexing and breaking its own windows. It was at risk of a catastrophic overturning failure, literally twisting itself off its foundation and toppling into the surrounding financial center. The public was terrified of the falling glass. Completely unaware that behind the black plywood sheets, engineers were realizing the entire skyscraper was structurally incomplete. The clock was ticking, the financial district was paralyzed, and the developers were facing total economic and physical ruin. The global architectural war, China's mega project Paranlisto, fully comprehend the sheer scale of the Copley Tower engineering crisis. You have to look at it not as an isolated disaster, but as the opening chapter in a brutal, multi-decade war between radical architectural design and the laws of structural physics. This is a conflict that has repeated itself across the skylines of China's most powerful economic engines, from the mudflats of the Pearl River Delta to the deep alluvial plains of Shanghai. The Copley Tower became the ultimate textbook warning, the foundational cautionary tale that every major modern high-rise project has had to reckon with. When structural forensic experts began unpacking the twin failures of the Copley Tower, the thermal destruction of its glass envelope and the aerodynamic twisting of its parallelogram frame, they realized that pushing the boundaries of vertical architecture always triggers the same terrifying variables. Extreme wind loads at high altitudes, unpredictable aerodynamic vortexes, unprecedented thermal stresses on materials that were originally engineered for low-rise buildings. Consider the similarities to another massive, high-stakes engineering crisis that gripped Shenzhen decades later, the sudden, unexplained swaying of the 70-story Seg Plaza in Huaqiangbei. In that disaster, a landmark tower suddenly began to vibrate violently on a clear day, forcing thousands of panicked tech workers to flee into the streets. Just like the Copley Tower, early theories blamed foundation settlement or structural degradation. But when the China Academy of Building Research deployed its top forensic teams, the structural data pointed to a much more complex culprit: vortex-induced resonance. Winds rushing past the top of the tower had synced perfectly with the building's natural harmonic frequency, magnified by massive, heavy mast antennas sitting on the roof. The building was literally acting as a giant tuning fork. The lesson that connected the Copley Tower to the Seg Plaza crisis was identical. A tower cannot simply be strong enough to support its own dead weight. It must be aerodynamically sculpted to survive the invisible. Violent rivers of air flowing hundreds of meters above our heads. The plight of the waterfront metropolis, the geographical vulnerability of the Copley Tower. Being built on loose, wet, 19th century maritime landfill, mirrors the exact engineering nightmares faced by the creators of the Shanghai Tower and the ultra-tall high-rises of the Pudong Financial District. Pudong, much like Shenzhen's coastal reclaims and Boston's historic Back Bay, sits on a thick bed of soft, waterlogged clay and silt, carried down by the Yangtze River. When engineers prepared to build the Shanghai Tower, they knew that if they built a traditional, rigid, flat-faced skyscraper, the immense wind forces from seasonal typhoons slamming into the building would transmit massive lateral loads down to the soft earth, causing catastrophic differential settlement, where one side of the building sinks faster than the other, tearing the concrete core apart to prevent the exact structural twisting crisis that quietly threatened to topple the Copley Tower. The architects of the Shanghai Tower had to completely abandon flat, geometric surfaces. They ran their designs through hundreds of advanced wind tunnel iterations, ultimately shaping the building into a highly complex, 120-degree twisting asymmetrical spiral. Traditional flat-faced tower generates massive alternating vortexes, extreme structural twisting. Asymmetric spiral tower disrupts and dissipates wind flow, 24% reduction in lateral wind load. That's single. Radical engineering choice disrupted the wind flow so efficiently that it reduced lateral wind loads by a massive 24%. That optimization didn't just save the tower from structural failure. It saved the developers over $58 million in structural steel reinforcements. Henry Cobb and the engineering teams of the 1970s did not have access to the advanced computational fluid dynamics that shaped Pudong's icons. They were flying blind into a new era of architecture, using slide rules and primitive physical wind tunnels to guess how 10,000 sheets of glass would react to a coastal storm. Glass. Wall. Crisis. In the ultra-dense Copley Tower disaster also forced a complete rewrite of how modern cities view T glass curtain wall, the non-structural outer skin of a building. In cities like Guangzhou, Chongqing, and Tianjin, where high-rises stand so close together that they form artificial wind canyons, a single falling window can turn into a weapon of mass destruction. When a 500-pound pane of glass breaks loose at 800 feet, it doesn't just drop straight down. The intense aerodynamic pressures around the building capture the flat sheet, turning it into a giant aerodynamic glider that can sail horizontally for entire blocks before slicing into the streets. Following the Copley Tower debacle, building codes across China and the world completely banned the use of rigid solder-bonded double-pane glass units on high-rise curtain walls without extensive dynamic testing. Modern towers like Guangzhou's CTF Finance Center or the CITIC Tower in Beijing are wrapped in highly advanced structural silicone glazing systems. These systems utilize flexible, high-durability polymers that allow each individual pane of glass to flex independently up to several centimeters, expanding and contracting safely under the brutal changes of solar heat and wind pressure. Every time you look up at a modern, seamless mirror tower in any major Chinese Tier 1 hub, you are looking at an evolution that was bought and paid for by the terrifying failures of the Copley Tower. The Plywood Palace proved once and for all that when you build at the bleeding edge of ambition, the tiniest factory oversight can transform a multi-million-dollar monument into a towering monument of public terror. The human cost on the streets of reclaimed land to fully understand the terror that gripped the district during the height of the Copley Tower crisis, you have to look past the corporate press releases and step onto the wet, crowded sidewalks of the Back Bay Financial Center. This wasn't an abstract engineering problem discussed in quiet university lecture halls. It was an active, unpredictable urban war zone. For the tens of thousands of commuters, workers, and residents moving through the district every day, the multi-million-dollar tower was no longer a symbol of modern progress. It was a looming, silver and blue guillotine. Let's put yourself in the shoes of Li Jun, a mid-level accountant working at a regional bank branch directly across the street from the rising glass structure. For Li and his colleagues, the winter of 1973 didn't start with professional milestones, but with a series of alarming, thunderous cracks that echoed through the concrete canyons of the business district. On the clear, freezing afternoon of February 5th, Li was walking back from a local noodle shop during the peak of the lunch hour rush. The coastal winds were gusting at a moderate 35 miles per hour. Nothing unusual for a winter day near the reclaimed waterfront mudflats. Suddenly, a sound like a high-caliber rifle shot rang out from the upper reaches of the Copley Tower. Li looked up just in time to see a massive 500-pound mirrored panel detach completely from the 52nd floor. Captured by the intense, swirling aerodynamic pressures generated by the building's sharp parallelogram corners, the quarter-ton sheet of glass didn't just drop. It glided. It sliced through the air like a massive, glittering razor blade, sailing horizontally across the width of a 4-lane avenue before slamming into the concrete facade of a neighboring office building. The impact was deafening. The insulated double-pane unit exploded into millions of heavy, jagged shards that rained down onto the crowded pedestrian crossing below. 52nd floor. Window fails, aero pressures, catch flat pane, sails horizontally, across 4-lane avenue. Massive pedestrian crossing. Millions of jagged shards, explodes against neighboring facade. Panic erupted instantly. Hundreds of commuters screamed, scattering into doorways and diving under transit shelters to escape the descending storm of razor-sharp glass, while Li managed to escape uninjured by scrambling under a heavy concrete awning. Several pedestrians were struck by the falling debris, suffering deep lacerations. By the time emergency vehicles and units from the municipal fire rescue services arrived to rope off the intersection, the sidewalk was covered in a thick, glittering blanket of blue-tinted glass shards, mixed with the mangled remains of aluminum window frames. The Plywood Palace evacuations and the 45 mph Barrack d'Issaz, the frequency of the failure accelerated into the spring of 1973. The local Public Security Bureau and the city's housing administration realized they were completely powerless to predict which window would fail next. The structural silicone and rigid solder bonds holding the Bondermetic Veritron units together were degrading at an exponential rate under the relentless daily cycles of solar expansion and nocturnal contraction. The city had no choice but to implement an unprecedented, humiliating safety protocol, the 45 mph lockdown. The Municipal Construction Commission established an emergency monitoring station equipped with high-precision anemometers, wind speed sensors, mounted to the roof of the adjacent commercial complex. The orders were absolute and unyielding. The moment the sustained wind speeds or localized gusts hit 45 miles per hour, an air raid siren would sound across the plaza. Instantly, traffic police would deploy heavy steel barricades, completely sealing off one of the busiest financial and cultural squares in the entire metropolis. Bus routes were abruptly detoured, paralyzing the morning commute for over 50,000 workers. Local shop owners were forced to lower their heavy metal security shutters and evacuate their customers, destroying the economic lifeblood of the district. Pedestrian corridors were lined with temporary, heavy timber tunnels, makeshift covered walkways built out of industrial scaffolding and thick wooden planks, designed to prevent a falling 500-pound sheet of glass from instantly crushing a citizen to death. Inside the building, the conditions were no better. Tenants who had signed expensive pre-lease agreements found themselves working inside a surreal, dark labyrinth, because more than an acre of the tower's mirrored surface had been shattered and replaced with thick, black-painted plywood boards. Entire floors were completely blocked from natural light. Employees operated under the harsh glow of industrial fluorescent lamps, staring at raw wooden backing where their panoramic views of the city skyline were supposed to be. Worse still was the terrifying psychological toll of the structural sway. On stormy days, before the perimeter streets could even be cleared, workers on the 40th floor and above would watch the water in their office coolers slosh violently from side to side. The slow, rhythmic, low-frequency oscillation of the flexible steel frame created an environment akin to the deck of a cargo ship trapped in a maritime storm. Dozens of high-level executives and administrative clerks reported severe motion sickness, vertigo, and vomiting. The situation became so intolerable that major corporate tenants openly threatened to default on their leases, packing up their files and moving their operations to older low-rise concrete complexes across town. $5 million landslide. Damon figures and litigation the economic damage caused by the Copley Tower disaster was an escalating landslide that threatened to drag every single company involved into complete bankruptcy. The initial construction budget for Henry Cobb's glass masterpiece was projected at a substantial but manageable $75 million. By the time the windows started falling and the structural core crisis was discovered, the final price tag skyrocketed past $175 million, more than double the original estimate, pushing the project over 5 years behind schedule. On September 15, 1975, the Hangsen Mutual Life Insurance conglomerate stopped waiting for excuses and filed a massive sweeping lawsuit in the municipal economic courts. They didn't just sue the glass manufacturer. They filed claims against a sprawling roster of 6 separate corporate entities that had touched the building. IM. Pei & Associates, the celebrated architectural firm, cited for negligent design and failure to specify materials capable of withstanding local coastal wind loads. Gilbane Building Company, the general contractor, accused of improper oversight and failing to maintain installation tolerances. H. Robertson, the specialized curtain wall subcontractor responsible for hanging the massive panels. Libby Owenson Ford, LF, the industrial glass manufacturer that designed and fabricated the fatally flawed Bondermetic Veritran units. The principal underwriting insurers, the financial institutions that had bonded the structural work. Hancock's total claimed damages came to a staggering $90 million. To break down the cold, hard financial data filed in the court records, approximately $11 million was designated strictly for the physical cost of tearing out and replacing all 10,344 windows with thick, single-pane tempered glass. The remaining $79 million consisted of massive consequential losses, including an explosive $25.9 million claim penalizing the contractors for the fact that Hangsen was completely unable to occupy or utilize its own flagship headquarters for 33 consecutive months. The legal warfare dragged on for 6 grueling years, generating mountains of conflicting engineering testimonies and secret laboratory reports. The defendants knew that if the full details of the factory testing failures and the secret wind tunnel data were made public, it would completely destroy their corporate reputations on a global scale. Finally, in August 1981, the parties reached a private out-of-court settlement for an estimated $30 million. The catch? Every single executive, lawyer, and engineer involved was forced to sign a draconian, lifelong non-disclosure agreement. The public had watched a multi-million-dollar skyscraper turn into a boarded-up public hazard in the center of their city. But the final accounting and the admission of structural fault were buried forever behind a sealed conference room door. No one apologized on the record. No one explained to the citizens of Shenzhen exactly who had failed them, leaving the true nature of the disaster to be whispered among structural engineers as a dark, off-the-record warning. The secret reinforcement and the lesson of the hidden core. Just when you think this multi-million-dollar architectural disaster could not get any more absurd, the story of the Copley Tower takes a turn that shifts it from a public nuisance into a terrifying case study of hidden structural risk. Because the falling 500-pound panes of glass that terrified the Back Bay district of Shenzhen for 4 straight years, they were never the thing that could have actually caused a mass casualty event. That was a completely different crisis, one that the developers, architects, and municipal officials fixed in absolute, crushing silence while the public's eyes were fixed on the plywood. Remember the emergency wind tunnel testing run by William Le Mesurier? When the aerodynamic data from the independent labs finally landed on the desks of the Hongsen executives and the Municipal Construction Commission, it triggered an immediate cold panic. The building's tall, thin, hyper-sharp parallelogram profile meant that under a maximum-strength coastal typhoon blowing off the South China Sea, the Copley Tower wasn't just going to lose its windows. It was vulnerable to a structural phenomenon known as P-delta overturning. The tower was at risk of twisting so violently along its vertical axis that it could deform its main structural columns, lose its equilibrium, and completely fall over into the center of the financial district. The architects immediately flew in Bruno Thurlemann, one of the world's leading authorities on tall steel structures, to verify the terrifying data. Thurlemann's calculations confirmed the worst. The building was structurally incomplete. It lacked the necessary torsional, or twisting, resistance to survive a worst-case seasonal storm. Sharp wind gusts hits acute parallelogram corner, creates violent vortex shedding. Catastrophic overturning, exceeds steel yield strength, severe torsional twisting. To save the tower from a potential catastrophic collapse, the construction crews had to execute an emergency structural intervention in complete secrecy. While the local news channels and citizens were laughing at the plywood palace and complaining about blocked sidewalks, engineers quietly snuck roughly 1,500 tons of heavy, diagonal structural steel, bracing into the central core of the building. Day after day, welding crews worked deep inside the utility shafts and elevator banks, reinforcing the building's skeleton from the inside out. The public never knew that the tower they were mocking for its broken windows was actively being prevented from toppling over onto their heads. The spreading risk in the era of luxury envelops the Copley Tower, now known simply by its municipal address. 200 Clarendon Street still stands today. The thick, single-pane tempered glass installed during the multi-million-dollar reglazing project has held firm for half a century. The heavy-tuned mass dampers, those twin 300-ton weights floating on a film of hydraulic oil near the 58th floor, still slide silently back and forth, canceling out the wobble of the coastal winds before the occupants inside can feel seasick. The tower has become a beloved icon of the skyline, widely praised for its minimalist beauty. But its legacy among structural engineers is far more sobering. It stands as the ultimate proof of a dangerous architectural truth. The structural failures you can see are almost never the ones that should actually scare you. A whole city watched the glass fall and completely missed the crisis with the steel. This leads us to a deeply uncomfortable question for our modern, hyper-dense urban eras. Right now, across the booming megacities of the Pearl River Delta, Yangtze River Economic Belt, and Beijing-Tianjin-Hebei tech corridors, there are thousands of towering glass monuments built at a breathtaking, unprecedented pace. Every year, developers push for sleeker profiles, thinner columns, and more radical, asymmetric geometries to capture the public's attention and maximize luxury floor space. But how many of those gleaming glass envelopes are hiding their own silent manufacturing flaws or aerodynamic anomalies? How many structures do you walk past every single day that are only standing because of an emergency, late-stage structural fix that the public was never told about? The physics of wind, gravity, and thermal expansion do not care about corporate prestige or architectural ambition. If a building is flexing to death from the inside out, the laws of structural engineering will eventually collect their debt, and they will collect it in full view of the streets below. Tell me which luxury high-rise, cracked mega-project, or sinking skyscraper you want investigated next. Drop the name of the tower in the comments below, and I will go digging into the forensic engineering records.